Hello everybody, good morning. Myself, Dr. Shubhankar Sen, an Associate Professor from the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the fourth lecture of Module 7 of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall consider the second part of marching problem. So we shall consider the hyperbolic partial differential equations where the velocity is present. In this connection, we shall consider the first order wave equation. We shall numerically solve this problem under the Galerkin FEM formulation in one dimension. We shall show that the resultant assembled matrix for this case, this is a skew-symmetric matrix signaling a fundamental difference with respect to the transient heat diffusion problems. So first we begin with the Galerkin weak form and the subsequent element level matrix development for the first order wave equation, which is a classic example of the hyperbolic partial differential equation. The first order wave equation is given by del u del t plus c del u del x equals to sx in one dimension. This is a classic example of a hyperbolic PDE. This is a problem of marching in time. So in this equation, the first term is the unsteady or the transient term. The second term is the convection term. And the last term is the source term. Here, this convection term is a linear term because we consider c as a constant. So c here, it represents the speed of the wave. C is a constant, and because of that, c del u del x is a linear term. If c is greater than 0, wave moves from left to right and vice versa. In this case, we see that this is a first order partial differential equation. The first order wave equation is a first order PDE, and hence its integral form also represents its weak form. In the above equation, u equals to u of space and time is the degree of freedom. Since the equation is of first order, we only have the primary variable and there exists no secondary variable. These we have already discussed in our previous classes. So we shall consider only the essential boundary conditions for this problem. So let us rewrite the strong form. The strong form of the first order wave equation may be rewritten as find u belonging to omega such that del u del t plus c del u del x equals to sx on omega cross tau, where tau is the time or temporal domain. Here u equals to g at gamma g1 and u equals to g2 at gamma g2. So these are the EBCs. No NBC is defined for this problem since there exists no secondary variable. In absence of the diffusion term. Now we derive the weak form by using the statement of method of weighted residuals. Derive the weak form using the statement of the method of weighted residuals given as integration over omega I w r uh d omega I equals to 0, where r is the residual. We know that r of this is the residual, equals to del del t plus c del del x minus sx. This is not equals to 0, and then the MWR gives integration over omega I w r d omega I equals to 0, or integration over omega I w into del del t plus c del del x minus sx d omega e equals to 0. In one dimension, we take d omega e equals to dx. So dropping the superscript h, we get integration over omega I w into del u del t plus c del u del x minus s dx equals to 0. Now we separate the known terms and the unknown terms. So source term is a known term. We shall certainly shift it to the right hand side. This gives us integration over omega I w del u del t dx plus integration over omega I c into w del u del x dx equals to integration over omega I w s dx. Since c is a constant, we can write integration over omega e w del u del t dx plus c integration over omega e w del u del x dx equals to s into integration over omega e w dx. So let us take s is also a constant. Now the trial solution for the degree of freedom may be given as u x t equals to summation u j e t psi j e x, as j is varying from 1 to n plus summation of u b e psi b e, where b belongs to the essential boundary. For Galerkin approximation, w equals to psi I e x. So w equals to wx. Now we substitute the Galerkin approximation as well as the trial solution in the above weak form. So this represents weak form of the first order wave equation. It has no boundary integral. Therefore, the integral form of the first order wave equation represents its weak form. We already discussed that the first order equations are not integrated, they are kept in the integral form, and this integral form itself is the associated weak form. So let us make the next simplification. Substituting w equals to psi I e and the trial solution expression in the weak form, we get integration over omega e psi I e del del t summation over u j e t psi j e plus summation over u b e psi b e, here j varying from 1 to n, here b is belonging to eta g. This is the trial solution portion dx plus c integration over omega e, w means psi I e for Galerkin approximation, del u del x is del del x into summation of u j e time psi j e plus summation b belongs to eta g u b e t b e dx equals to s into integration over omega e psi I e dx. We can simplify this as summation over j equals to 1 to n psi integration over omega e psi I e psi j e, here it is dx into del u j e del t plus summation over b belonging to eta g psi ie psi be integration over omega e dx del tbe del t plus for the convection term we have the constant outside summation j equals to 1 to nen psi ie integration over omega e del psi j del x dx into uj plus c into summation over b belongs to eta g integration over omega e, this is psi be psi ie del psi be del x dx into ube equals to s into integration over omega e psi ie dx. Now the shape function psi, this is a function of x only, and the degree of freedom u, this is a function of time only. This is our choice. So psi is a function of space only, and the nodal value uje is treated as function of time only. Therefore, we can simplify the equation as summation over j equals to 1 to nen, j equals to 1 to nen integration over omega e psi ie psi j dx d uj dt plus summation over b belongs to eta g integration over omega e psi ie psi be dx dube dt plus c the summation over j equals to 1 to nen psi ie d psi j dx integration over omega e dx uj plus c into summation b belongs to eta g integration over omega e psi ie d psi be dx dx ube equals to s into integration over omega e psi ie dx. So this will be ube so here now this particular form of the weak form obtained after spatial discretization is known as the semi-discrete form. The semi-discrete form represents an ordinary differential equation or ODE in time. This we have already discussed in the first lectures of this module in conjunction with the unsteady parabolic partial differential equation. Now we introduce the symbols for the element level entries. So let us define integration over omega e psi ie psi je dx equals to mij equals to element level mass matrix. Then integration over omega e psi ie psi be dx equals to m ibe mass matrix contribution due to unsteady or time dependent essential boundary condition. The next term is C into integration over omega e psi ie d psi je dx equals to C ije equals to element level convection matrix. C into integration over omega e psi ie d psi be dx equals to C ibe equals to element level convection matrix contribution associated with EBC. And finally we have S into integration over omega e psi ie dx equals to element load vector due to source term. So with incorporation of all these definitions, the semi-discrete form may be represented as the semi-discrete form of first order wave equation at element level is given by summation j equals to 1 to nen mij d uj dt plus summation over j equals to 1 to nen c ij uj equals to fie minus summation over b belongs to eta g m I be d ube dt minus summation over b belongs to eta g c I be ube. So this is the first portion, contribution due to unsteady term. The second term, this is the convection matrix contribution due to convection term FIE. This is due to source term. Here, the second part in the right hand side, this is due to unsteady EBC. Due to unsteady EBC, and this portion, this is because of EBC. Okay, so these BC portions, they are the known terms, boundary conditions. So we have shifted them to the right hand side. So the final element level matrix is given in compact form as ME due dt plus CE UE equals to F tilde E. So the entire right hand side portion, that is coming under F tilde. After assembly, this equation may be presented as M du dt plus C U equals to capital F. So size of the mass matrix, this is the assembled mass matrix, assembled convection matrix, assembled load vector. The mass matrix M, this is a square matrix of size P into P or P into Q. Here P is global equation number. In the element level, the element level mass matrix ME is of size NEN by NEN. ME NEN by NEN. So number of nodes per element, because we have only 1 degree of freedom per node. Now we shall calculate the convection matrix for the first order wave equation for the two-noded bar elements. There is no diffusion matrix because in the first order wave equation there is no diffusion term. Since there is no diffusion term present in the first order wave equation, we do not get any diffusion matrix or stiffness matrix Ke. So let us evaluate the convection matrix CE for a two-noded bar element. So we have CE equals to Cij equals to C11E C12e, C21e, C22e for a two-noded bar element. The local nodes are 1 and 2. The mesh size is delta x. Now we have from the definition Cij equals to C into integration over omega e psi ie d psi je dx. So we can shift the limit of integration from the physical coordinate to the master coordinate by the coordinate transformation. We can write this expression as C into integration over omega e cap psi ie xi d psi ie xi d xi dx, determinant of the Jacobian into d xi equals to C into integration from -1 to 1 psi ie xi d psi je xi d xi this portion is equals to 1 and we have d xi. Now we know that psi 1 is xi equals to half of 1 minus xi. This gives d psi 1 d xi equals to minus half, psi 2e xi equals to half of 1 plus xi. So this gives us d psi 2e d xi equals to half. So for I equals to 1 and j equals to 1, we get C11e. C11e equals to C into integration from -1 to 1 psi 1 is xi d psi 1 e xi d xi d xi. This is equals to C integration -1 to 1 psi 1 is xi is half of 1 minus xi d psi 1 e d xi. This is minus half into d xi. So this gives us minus c by 4 integration -1 to 1 xi minus 1 d xi. After simplification we get minus c by 4 into xi square by 2 minus xi varying from -1 to 1 minus c by 4 into half minus 1 minus half plus 1. This is giving us minus c by 4 into half minus 1 minus half minus 1. So this will be plus, 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 plus. So here we have equals to c by 4 into minus 2 equals to minus c by 2. Similarly, for I equals to 1 and j equals to 2, we get C12e equals to C integration -1 to 1 psi 1 is I into d psi 2e d xi equals to C integration -1 to 1 half of 1 minus xi into half into d xi equals to minus c by 4 integration -1 to 1 into xi minus 1 d xi integration xi minus 1 d xi minus c by 4 into minus 2 equals to c by 2. So we have calculated the first row. We expect asymmetry because of this convection term. So we expect that C12E not to be equal to C21E. Let us find it. Let us check it. For I equals to 2, j equals to 1, we get C21E equals to C into integration minus 1 to 1 psi 2E xi d psi 1E d xi d xi. So this is C integration minus 1 to 1 psi 2E xi is half of 1 plus xi, and this is minus half d xi. So this gives us minus C by 4 integration minus 1 to 1 plus xi d xi. This is equal to minus C by 4. Then after integration we get xi plus xi square by 2. The limit is minus 1 to 1. This is minus C by 4 into 1 plus half minus 1 plus half. This is minus C by 4 into 1 plus half plus 1 minus half. This is equals to minus C by 4 into 2. So this is minus C by 2. So we find that this C12E, it was plus C by 2, and we get that C21E is not equals to C12E, and therefore as our expectation we find that the 2 by 2 matrix at the element level, it will be asymmetric. Therefore C12E is not equals to C21E, or the 2 by 2 CE matrix must be asymmetric as expected because of the presence of the convection term. Now we are left with the last term. So for I equals to 2 and j equals to 2, we get C 2 to E equals to C integration from minus 1 to 1 psi 2E d psi 2E dx equals to C integration minus 1 to 1 half of 1 plus xi into half d xi. So this is equals to C by 4 integration minus 1 to 1 plus xi d xi equals to C by 4 to xi plus xi square by 2 varying from minus 1 to 1. This is equal to C by 4 into 1 plus half minus 1 plus half. This is C by 4 into 1 plus half plus 1 minus half. This is equals to C by 2. Therefore, the element level matrix for convection CE equals to C11E, C12E, C21E, C22E. So the first term, it was C11E. C11E was minus C by 2. So this is minus C by 2. The second term C12E, this is C by 2, and C21E is minus C by 2. So we get C by 2 minus C by 2, and C22E is C by 2. So we see a very interesting result that for the element level convection matrix with the two noded bar elements, our rows are exactly identical. It means that this is a linearly dependent matrix. The rows of the convection matrix at element level are identical. Therefore, the convection matrix CE must be linearly dependent. We can see here determinant of CE equals to minus c square by 4 plus c square by 4 equals to 0. So this is a singular matrix as expected for a linearly dependent case. So CE is linearly dependent with identical rows, and also CE is asymmetric. Then we find another feature that CE has a negative term on the diagonal. This negative term will have a very interesting consequence on the assembled convection matrix, given that C11E and C22E are of the same magnitude but have opposite signs. So let us consider the conduction or diffusion matrix at element level for a two-noded bar element. We know that Ke equals to K by delta x minus K by delta x minus K by delta x and K by delta x. During assembly, the diagonal terms are added. The assembly of Ke leads to K by delta x plus K by delta x equals to 2K by delta x terms along the main diagonal of the global stiffness matrix. Accordingly, the global convection matrix will have minus c by 2 plus c by 2 equals to 0 along its main diagonal. To illustrate this, let us consider 5 elements with EBC at the boundaries. So we shall consider 5 elements. This we have done many times in this course. So global node 1, 2, 3, 4, 5, 6, and our elements are 1, 2, 3, 4, 5. This is x equals to 1. This is x equals to 0. So EBC at x equals to 0, and EBC also at x equals to 1. So these are our global nodes, and these are our elements. Now we generate the ID array. So this is for the global equation numbers 0 and 0, and we have intermediate nodes with 4 equations: equation 1, equation 2, equation 3, equation 4. So our degrees of freedom, they are U1, U2, U3 and U4. So these are the global equation numbers. So P is global equation number. Now we can easily perform the assembly for a generation of 4 by 4 matrix. So our elements, we can show a generic element, element E, local node 1, local node 2. The degrees of freedom are U1E and U2E. We got the convection matrix, the element level convection matrix CE equals to minus C by 2, C by 2, minus C by 2 and C by 2. So we want to construct the global convection matrix capital C. So generate global convection matrix capital C of 4 by 4 size. So capital C equals to C11, C12, C13, C14, C21, C22, C23, C24, C31, C32, C33, C34, C41, C42, C43, C44. This C11, it will be C221 plus C112. Then C12, it will be C122, C122. Let us give the element numbers 1, 2, 3, 4 and 5 for the last element. So C13 and C14, they will be 0, 0, 0. C21, it will be C212, C212, C22, it will be C222, C222 plus C113. Then we have C23, C23 will be C123, C123, last term is 0. Then here we have C31, C31 is 0. Then we have C32. So C32 will be C213, C213. Then we have C33. C33 is C223, C223 plus C114, C34. This will be C124, C124. Finally, the last row we have C41 and C42, both 0. Then C43 equals to C214, C214, and C44 equals to C224, C224 plus C115, C115. Now we put the numbers and generate the matrix. So C221, C221, this is C by 2. C112, this is minus C by 2. C122, this is C by 2. Remaining terms are 0 in the first row. Then we go to the second row. C212. C212 is minus C by 2. So this is minus C by 2. The diagonal term is C222. C222 is C by 2 plus C113. C113 is minus C by 2. Next is C123. C123 is C by 2. The last term is 0 in the second row. Then we come to the third row. First term is 0. Then it is C213. C213 is minus C by 2. Minus C by 2. Then we have the diagonal term. It is C223. This is C by 2. Next is C114. So it is minus C by 2. The last term in the third row, this is C124. This is C by 2. Then in the fourth row, we have 2 zeros. Next is C214. This is minus C by 2. And the final diagonal term is C224 plus C115. This is C by 2 minus C by 2. So here we have the matrix terms. So the final terms, we can write it as C by 2 minus C by 2. It is 0. Next is C by 2. Next is 0 and 0. Then we have minus C by 2, 0. C by 2, 0. Then we have 0 minus C by 2, 0. C by 2. In the last row, we have 0, 0 minus C by 2 and 0. So we have generated the 4 by 4 matrix. We can rewrite this expression here. The assembled convection matrix is C equals to 0, C by 2, 0, 0 minus C by 2, 0, C by 2, 0, 0 minus C by 2, 0, C by 2, 0, 0 minus C by 2, 0. So we can write it as C by 2 into 0, 1, 0, 0 minus 1, 0, 1, 0, 0 minus 1, 0, 1, 0, 0 minus 1, 0. So this is the final form of our convection matrix. It is very interesting to see that all the diagonal terms are 0 and Cij equals to minus Cji. So this represents that the global matrix for convection, this is a skew-symmetric matrix. We note that C11 equals to C22 equals to C33 equals to C44 equals to 0 and Cij equals to minus Cji. This represents the features of a skew-symmetric matrix. These are features of a skew-symmetric matrix. So the assembled matrix C, assembled convection matrix C is skew-symmetric. It is also not diagonally dominant because of presence of zeros along its main diagonal. Diagonal dominance may be achieved by swapping the rows. It is very interesting that despite the skew-symmetric nature or the presence of zero diagonals on the assembled convection matrix, we can still have solutions for this problem. We shall show this, the solution for one-dimensional wave equation of hyperbolic type. So we shall show that the explicit calculations do not work, whereas the implicit calculations, they give us the converged results. Now we go for numerical solution. As an example, hyperbolic PDE problem. So we shall consider the same governing equation, del u del t plus c del u del x equals to the source term within the domain 0 to 1, and then our wave speed is given as 1 meter per second and the source term value is also 1, and both the boundary conditions are of essential type. So the left hand side boundary, this is a homogeneous boundary, and the right hand side boundary is a non-homogeneous boundary, and we use this as a model problem for one dimension with 5 elements or the 6 global nodes. So this is our problem definition, that del u del t plus c del u del x equals to the source term. This is x equals to 1 unit, x equals to 0. Here this is u equals to 0 at x equals to 0, and here u equals to 1 at x equals to 1. Both are the essential boundary conditions, and we have the mesh here. So we have 5 elements, 5, element 1, 2, 3, 4, 5, and we have global nodes 1, 2, 3, 4, 5, 6. These are our global nodes. These are our elements. This is the x direction. So this is x equals to 1 and this is x equals to 0. In the previous lectures, we have already constructed the mass matrix for the two-noded bar elements at the element level and also at the assembled level. So here we are getting the element level mass matrix. This is containing 1 by 15, 1 by 30, 1 by 30 and 1 by 15. And similarly, after assembly, we get the tridiagonal mass matrix at the assembled level, which is symmetric. And we also know that for the value of s equals to 1, the load vector per element per node, it is delta x by 2. So Fe equals to s into delta x by 2, delta x by 2. Since our s is 1 unit, so we are getting Fe equals to half of the mesh size for every element. This is contribution from the source term. So this is contribution from the source term. In the question, this phi, it should be replaced by degree of freedom u. So one important aspect for this problem is that our governing equation, this is a first order partial differential equation both in space and time. The differential equation is first order both in space and time. So we need one initial condition and only one boundary condition. So in this case, we merge both in space and time. We give inlet boundary condition and at exit we find the solution. Now we have just now shown the convection matrix at the element level. This is a finite element E, local nodes 1 and 2. This is degree of freedom U1E. This is U2E. Here we have the element level convection matrix CE equals to minus C by 2, C by 2, minus C by 2 and C by 2. Then we can perform the assembly based on the LM array. For the given mesh, we can generate the LM array as E. A. E is varying from 1, 2, 3 4, 5. A is 1 to 2. Our IDOF is 1. A number of element equations. This is 1 to 2. So we have the global equation numbers present in the boxes. So first and last nodes, they are of essential type. Equation number is 0, 1, 1, 2, 2, 3, 3, 4, 4 and 0. So from here we can generate the assembled matrix capital C for the convection. So capital C, it is already shown as C by 2 into 0, 1, 0, 0, minus 1, 0, 1, 0, 0, minus 1, 0, 1, 0, 0, minus 1, 0. The assembled convection matrix. The matrix C is non-singular. It is linearly independent. Determinant of this matrix 0, 1, 0, 0, minus 1, 0, 1, 0, 0, minus 1, 0, 1, 0, 0, minus 1, 0. This is found to be 1. Because of that, this matrix is linearly independent and we can solve the problem despite having zeros along the diagonal. Now, our semi-discrete global matrix equation system is M du dt plus Cu equals to F. So this semi-discrete equation, it can be time integrated by using explicit, implicit, Crank-Nicolson, Galerkin schemes, etc. So if we perform the explicit scheme, for example, we can write it as for explicit time integration M u at n plus 1 minus u at n by delta t plus c u at nth time level equals to f at nth time level. So this is for the explicit scheme where n equals to time step count. Now here we have shown the assembled matrix, the load vector capital F. This is obtained after implementing the essential boundary conditions. So we have obtained this capital F equals to F21 plus F12 minus C 211 Q11. Then for the second, third and fourth rows we had F22 plus F13, F23 plus F14, and finally we have F24 plus F15 minus C 125 U2 5. This is the assembly relation. Our load vector will be calculated here after implementation of boundary condition as CE equals to minus C by 2 minus C by 2, and here it is C by 2. So C211, this is minus C by 2. So this term, this is C211, and this is U11. The last row, we can see that this delta x, it came as F24 plus F15, and this final term, this is C125 into U25. So this is C125 into U25. C125, this is C by 2. So our F24, it was delta x by 2. F15 is also delta x by 2. For convenience, we can show the equation numbers once more here. So this is 0, 1, 2, 3, 4, 0. These are our global equation numbers P. These are elements 1, 2, 3, 4, and the fifth element. So here we have considered a time step size of 0, 1. So delta t we have taken little big, and then we have considered the trivial initialization. So 0 initial guess. So this is 0 or trivial initial condition for the degree of freedom U. Now we shall perform the time stepping under the forward Euler or the explicit scheme. Here we are showing the time stepping here. Here this is the global mass matrix. This is the new DOF or updated DOF. This is the global mass matrix, and this is initial condition for DOF. This 0.1, this is our time step size, and this our load vector F. So this is delta t. This is our assembled convection matrix, and this is our initial condition for U. So performing this computation, we find the first level solutions. Then using the first level solution, we get the second level solution, and then here after large number of calculations, it is eventually found that these solutions, they diverge. So we have shown the divergence of the solutions below in two pictures for two different time step size. So here we have taken dt equals to 0.1 at all four unknown nodes. Then we find that the degrees of freedom, they are showing divergence. So divergence of results using forward Euler or explicit scheme using delta t equals to 0.1, we have considered a very small time step delta t equals to 0.001, that is shown here in figure B. So in this case also we have found that the results are diverging. It means that for explicit scheme, the solutions, they do not converge for this problem, and delta t equals to 0.001. So this is shown in the second case. The first order wave equation in the unsteady state, the solution of which was not achieved using the explicit scheme, is now attempted using implicit scheme. We have used the delta t value of 0.1. With delta t 0.1, we did not achieve solution. So we achieved solution using a smaller time step of delta t equals to 0.01. Some of the calculations are shown here. So here we have used delta t equals to 0.01. This is our consistent mass matrix. This is our delta t. This is our assembled convection matrix. This is the degree of freedom which we are calculating right now, the unknown DOF at level 1. This is again the mass matrix. This is our DOF at initial condition. This is again delta t, and this is our load vector F0 at the initial time level. Simplification gives us the AX equals to B matrix equation system, which we solve by using Gauss-Seidel method. This matrix equation system is found to be diagonal dominant. The matrix A is diagonal dominant and asymmetric. We use Gauss-Seidel method to find the solution, and the first step solution is shown here. So we have got these values which I am indicating. Using this first level solutions, we get the subsequent solutions. Some of the results are shown for the second level, third level, fourth level, and so on. Finally, we show the results for the converged case. So converged results obtained using delta t equals to 0.01 and Gauss-Seidel iterative solver. So this is delta t equals to 0.01. This was our problem. So this is global node 1, global node 6, global node 2, global node 3, global node 4, and global node 5, elements 1, 2, 3, 4, and 5. We have used u at 0 equals to 0 and u at 1 equals to 1. Using this, we have got the solution. So here at global node 2, the value which we get, that is u2 equals to 0.2. Here we get u3, this is 0.4, u4 equals to 0.6, and here u5 equals to 0.8. So here u2 corresponds to the first unknown node. So we got the solution. Here if we plot it as u versus x, so we got steady state solution. So here at x equals to 0, our solution is 0. Then at x equals to 0.2, 0.2, 0.4, 0.6, 0.8, and 1. At x equals to 0, our u is 0. At x equals to 0.2, our u is also 0.2. At x equals to 0.4, our solution is also 0.4. At x equals to 0.6, our solution is 0.6. At x equals to 0.8, our solution is 0.8. And at x equals to 1, our solution is equals to 1. So we get a straight line for the solution. So this is the solution, u equals to x. We get this kind of a solution, we get a linear distribution. So when x equals to 0.2, our solution is also 0.2. So we get y equals to mx kind of a relationship. So this is the solution curve. Now, if we use homogeneous boundary conditions at both the boundaries, consider homogeneous EBC at both the boundaries. So this is our bar. We have x equals to 0, x equals to 1. So del u del t plus c del u del x equals to sx. Here u0 equals to 0 and u1 equals to 0. So here we have just shown the solution in this picture. So this is the solution for homogeneous EBC at both boundaries. So we see that in both cases we got steady state solution. We got steady state solutions, or the solutions, they do not depend on the time level. So here we got u2 equals to minus 0.8, u3 equals to minus 0.4, u4 equals to 0.4 and u5 equals to 0.8. So we get some solutions in the negative direction and some solutions in the positive direction. So one wavy distribution of the steady state solution we get for the homogeneous boundary condition. We have used the same governing equation and the same equation solver and the same implicit discretization. So implicit discretization with delta t equals to 0.01 and Gauss-Seidel iterative solver. So we end our class today here with the numerical example on first order wave equation, which is a classic example of the hyperbolic partial differential equation. In today's class, we have discretized the first order wave equation using Galerkin formulation. The assembled convection matrix for this hyperbolic PDE using two noded bar elements is found to be skew-symmetric, while explicit method fails to yield converged solutions. For this problem, the implicit method works successfully. We have considered two sets of EBCs: homogeneous and non-homogeneous in other case both EBs is homogeneous. For today's class, the reference texts are by Professor T.J.R. Hughes and Professor J.N. Reddy. Thank you very much for attending my lecture.